Einstein's theory of relativity is an icon for the baffling side of 20th century science. Abstract, mathematical, notoriously difficult to grasp. It's given us such mind-numbing oddities as time warps, curved space, black holes, big bangs, and singularities. Yet this theory is now an established part of mainstream physics, taught to every undergraduate. It has even given us practical applications. So what's all the fuss about? Paul Davies, together with quantum mechanics, the theory of relativity is one of the twin pillars of modern physics, and like quantum mechanics, makes some very weird predictions. It must now be almost a century old. I understand that none of its predictions have been disproved. And I also note that although E equals mc squared pops up on an awful lot of t-shirts, that very few of us begin to understand what relativity really means. Would you be kind enough to give us the Reader's Digest condensed version of the special theory?
Right. Well, the special theory of relativity, which was published in 1905, is a theory of space, time, and motion. And in a nutshell, it says that if you move close to the speed of light, strange things happen to space and time. The speed of light is a barrier in this theory. It's the fastest speed that an object can move.
I find that immensely frustrating.
Yes, well,
please tell
science
me
fiction
why
writers,
may I
of course,
not go faster?
Well, supposing you try and do it, supposing you try and make something travel faster than light by accelerating it. Physicists routinely do this in the laboratory. They have giant accelerator machines and they whirl subatomic particles around them at very high speeds. Now, if you just keep pushing and pushing and pushing, what happens is that instead of the particles going faster and faster, they just get heavier and heavier. And this is one of the manifestations of this famous E equals mc squared. What happens is that the energy of motion gets converted into mass. So it acts like a barrier. The speed of light is like a barrier. The particles just get heavier and heavier. You can't push them on through that speed. And people often say, well, why not? Why can't you push them through the light barrier? Why can't you break the light barrier? And the answer is, well, you know, it's a law of nature. I don't know what else to say. That's just the way nature is. It is structured in such a way that the speed of light is an absolute barrier to motion.
I had no idea that the special theory was such a doddle. What about the general theory, which was added, what, about 10 years later?
Yes, about 1915. Einstein struggled to put it together over a number of years. It was very much a personal effort, whereas the special theory had been a sort of combination of contributions. The general theory of relativity is also a theory of space, time and motion, but it includes the effects of gravitation. Now, Einstein had this brilliant insight that gravitation isn't a force. That's what Newton, of course, told us, the force of gravity. Einstein said, no, it's not a force at all. It's actually a warping or a distortion of the geometry of space-time. Sounds very mysterious, doesn't it? But it's actually quite an easy idea. What it means is that we learn the rules of geometry at school, and we think of space-time as flat in the sense that it obeys in 3 dimensions the same rules of geometry as you learn on a flat sheet of paper with triangles and the angles adding to 180 degrees and so on. But it turns out that gravitational fields have the effect of changing those rules to introduce a sort of curvature or distortion in this geometry. And crudely speaking, the stronger the gravitational field, the more the space-time is bent or curved. And basically, it is a theory tying together, therefore, gravitation, space-time, and motion into one grand theory.
Paul, are there any technological whistles and bells, any gizmos that you could tell us about which exploit the theory?
Yes, indeed, there are. When Einstein first published it, he predicted a number of rather tiny effects in the solar system. For example, it was known that the orbit of Mercury is a little bit peculiar in the way it twists over time, but it's a very tiny effect. He was also aware of the fact that a starbeam passing close to the sun is very slightly curved or bent. So if you look at the position of a star in the sky when the sun is over there, it's slightly different from when the sun is over there. It's almost like looking at the sky through a type of lens. But again, it's a tiny, tiny effect. It can just be measured. So there were these small effects, but it didn't seem to be any big deal. And for a long time, people thought, well, the general theory of relativity was quite interesting because it did predict these tiny effects, but it had no practical value. But today, with our modern instrumentation and electronics, even these tiny effects become important. And the classic example is the global positioning system, which owners of yachts and even small boats use to find out where they are on the Earth's surface, to a precision within a few meters. Now, this has to take into account these general relativistic effects. And if you didn't, I'm told that you'd be out by up to 15 miles in your positioning. So it is a measurable and noticeable effect with real practical value.
You've mentioned that Newton was wrong with his theory of gravity. But wasn't Newton's theory nonetheless a magnificent approximation?
Yeah, there's no doubt about it that Newton's theory of gravitation is good for almost all purposes. It's good enough to send a spacecraft to the moon, for example. And it is only where the gravitational fields become very strong or where you need super precision, such as with an aircraft navigation or your yacht on the ocean, that the general theory comes into its own. Now, a lot of people say, well, what was wrong with Newton's theory? Can't we just go with that? You know, why did it have to be changed? Why did Einstein unpick that? And there's a very good reason for that, that the Earth moves around the Sun in a curved path because of the Sun's gravitational pull. Imagine that by some magic we could make the Sun go away, just like that. What would happen? Well, of course, the Earth would then just wander off through the galaxy. But it takes 8.5 minutes for light to reach us from the Sun. So if we made the Sun go away now, we wouldn't see anything for another 8.5 minutes when the Sun would disappear. But according to Newton's theory, the Earth's orbit ought to change instantly. And therefore, in Newton's theory, gravitational effects propagate instantaneously, but we've already discussed that nothing should travel faster than light, including forces and physical influences. And so, in Newton's theory, gravity effectively propagates at an infinite speed, and that isn't allowed. So Einstein had to adapt Newton's theory. You see, Newton's theory is good for when the gravitational fields are weak, but as soon as they become strong, you get not only mind-bending effects, but space and time-bending effects. But the black hole, I guess, is the classic example of where intense gravitational fields lead to really peculiar effects.
Paul, what is a black hole?
The name says it all. It's a region of space and time which is both black and empty. Now, how do you form such a thing? One way is if a star runs out of fuel and collapses under its own weight, and nothing can prevent it shrinking down to effectively no size at all. Then, under these circumstances, the gravitational field will become so intense that it even traps light. And seeing as we've discussed, nothing can travel faster than light, it traps everything else as well.
Well, let's imagine we're meandering in the vicinity of a black hole and we are sucked into it. What do you hypothesize happens?
Nobody really knows what happens if you fall into a black hole, except that we're pretty sure that you can't get out again. You can't get out for the same reason we've been discussing. You can't travel faster than light, and if light itself is trapped, then you are trapped. Now, if you take the mathematical theory as your guide, then at the center of the black hole is what we call a singularity, which is where the original star would have imploded to literally nothing at all. The entire matter of the star is compressed into a single point of infinite density, known as a singularity. And it seems that you would be inexorably drawn to that singularity, and in fact it would all happen rather rapidly in less than a microsecond. You would hit the singularity and be completely obliterated. So it looks like falling into a black hole is a one-way journey to nowhere. But we can't be completely sure of that, because it's entirely likely that at some stage before that singularity forms, the theory of relativity breaks down and is replaced by something else, and so we know not what.
Let's go back to the famous equation on the T-shirt. Is there any aspect of it that is yet to be tested?
Well, there's one that people have been working on for quite some time, and that's the existence of gravitational waves. Now, these waves would be like ripples in space-time itself. The theory predicts that they should travel at the speed of light and carry an immense amount of energy, but their effect is so feeble on ordinary matter that they are almost impossible to detect. You need fantastically sensitive technology to pick up these waves passing through the lab.
How fantastic?
Well, to give you some idea, supposing you have a chunk of metal this sort of size, a gravitational wave passes through it and it causes the metal to wobble about. Well, the level of sensitivity, the degree of wobbles that you have to detect, is equivalent to measuring a change in the distance from here to the nearest star of one human hair's width.
Is anyone working on a methodology to do this?
Oh, absolutely. There have been people working for some years, including right here in Australia, David Blair and his group at the University of Western Australia, working on these resonant bar detectors. You take a bar of aluminium, suspend it in a vacuum very delicately and see if it shakes and shudders. Of course, you have to isolate it from seismic disturbances and noise and so on. But a better technology is to use a laser system. You have basically a pair of mirrors in an L shape, and you send laser beams off to these two mirrors and bounce them off and compare the time of flight. This would be a more sensitive way of doing it, and these sorts of systems are being built around the world now. Nobody's yet detected a gravitational wave, but we're pretty sure they exist, not only because Einstein predicted them about 80 years ago, but also that there's a double star system called a binary pulsar. It consists of two neutron stars orbiting around each other, and the orbit of these stars is decaying very slowly, but the rate of decay matches exactly Einstein's formula for the energy drain if gravitational waves are being given off. It's a little bit like before you discover the existence of radio waves, somebody gives you a radio transmitter, you plug it in and you notice your electricity bills are going up. The energy must be going somewhere, so presumably it's going off in gravitational waves.
Can you imagine a consumer benefit coming out of this particular technology?
I don't think it's going to be the sort of bonanza that we got from electromagnetic waves, like radio waves, where we have radio technology. However, the astronomers are very keen to develop this because it's going to open up a whole new window on the universe. You see, we have telescopes that use light and radio waves, gamma rays, and so on. We've done the whole of the electromagnetic spectrum. This would be an entirely new spectrum. You could see things with a gravitational wave telescope that you could never see with any optical or radio telescope. You could, for example, study the coalescence of these two stars as they orbit together and finally merge and maybe form a black hole. You could look at the heart of quasars, very energetic objects that are probably black holes eating material in their vicinity. So basically, gravitational waves let you look at things that you could never see in any other way. And I'm sure it's going to be the trailblazing technology for astronomy in the 21st century.
If Einstein was currently a student in the Australian education system, I think the special theory would get him 10 out of 10 and a koala stamp. But you're not entirely satisfied with it. What's wrong with the theory?
Well, I think the special theory is in good shape, but the general theory of relativity, which includes gravitation, can't be the last word. The main problem here is that the other of the twin pillars of 20th century physics you mentioned, quantum mechanics, doesn't rest easily with the general theory of relativity. If you try to put the two together, to use the jargon, if you try to quantize gravitation, what you get is mathematical nonsense. Mostly you just get infinite answers to well-defined questions. And so clearly there's something gone wrong. There have been all sorts of attempts during my career to fix up either the one theory or the other to make it work. It's a little bit like a shotgun marriage. You know, you're taking two theories, each of which is mathematically consistent and very beautiful and confirmed by experiment. Try to fit them together. They don't want to be married up, so you try to force them together. That's obviously unsatisfactory. It would be much better either to change the one theory or the other, or maybe both theories. Perhaps both are some approximation of some deeper level of theory. And there are various ideas around. The one that's making all the running at the moment is called M theory, which is an attempt to build up a theory of space-time and matter in terms of membranes. This is an elaboration of the earlier string theory, that maybe the whole world is made out of little loops of string that wiggle around. Well, perhaps it's made out of little membranes that flap about. I think we all recognize that space and time, which for Newton were just the arena, they were just there, for Einstein became part of the dynamics. They themselves can change and move and are involved in the action, that these concepts of space and time ought somehow to come out of the theory and not to be put in as part of the tools of the trade.
Now this is tantalisingly close yet elusive.
Well, it's a little bit difficult to say how close it is. If you talk to the people working on something like M theory, of course they're gung-ho and they reckon that the problems will be wrapped up in pretty short order. I think to be realistic, we are a long way from having a fundamental theory that gives us not only gravitation and quantum physics, but space and time as well.
Is the universe still a bit like the blind man and the elephant? I mean, in other words, is it still open for debate at this level?
Yes, there is no doubt that we've got these bits of physical theory. We've mentioned quantum mechanics, we've mentioned gravitation and something like the general theory of relativity. There are other areas as well, like, for example, thermodynamics. And each is pretty successful in its own domain. The problem is to integrate these in some way. And the biggest clash is really between quantum mechanics and gravitation. That's
it was a clash, of course, that Einstein felt to his dying day.
Well, you see, Einstein never believed in the quantum mechanics, and his hope was that his theory of gravitation, his general theory of relativity, if suitably developed, could explain all this quantum stuff. And he tried very unsuccessfully to formulate a grand unified theory towards the end of his life that would include some of these quantum effects, or at least would be give us a level of theory deeper than those quantum effects and show that all those funny quantum things didn't really happen at some deeper level.
Paul, I feel us being drawn back towards the black hole. Can you describe Hawking's black hole evaporation effect?
Well, Stephen Hawking had the idea that even though quantum mechanics and gravitation don't fit together in a mathematically consistent way, you can nevertheless make a start. That is, you can apply quantum mechanics to a specific object like a black hole and see how you get on. And it turns out that you do get a sensible answer when you do that. What you find is that the black hole is no longer black, but emits radiation. In fact, a very distinctive type of radiation. It's heat radiation. It has the thumbprint, the spectrum of a body which is in thermodynamic equilibrium, that is at a uniform temperature. So it glows just like an oven that's been allowed to come to a common temperature. So you ask the question, if the black hole is emitting heat, if it's glowing, where is the energy coming from? E equals mc squared again. The energy can only come from the mass of the black hole. But the size of the black hole is determined by its mass. If the black hole loses mass, it shrinks in size. So in order to glow with this heat, the black hole has to shrink. Now, it's a very slow process, I might say. Even a black hole as small as the nucleus of an atom takes the entire lifetime of the universe to evaporate away, but eventually it will. It shrinks in size at an escalating rate and eventually disappears in a puff of radiation. So this is the ultimate vanishing act. You have a star which implodes and forms a black hole and disappears from the universe, and then the black hole itself disappears up its own space-time.
When Carl Sagan was still with us and he decided to try his hand at a novel, he wrote Contact. In Contact, he speculated on wormholes. And it was interesting that the fiction then was given some degree of scientific validation. More recently, Jodie Foster has been running around in the film version and at one point takes a very exciting ride across the galaxy through a wormhole. Possible?
Just about. A wormhole is a bit like a black hole. It's an adaptation of a black hole. Earlier we were discussing what happens if you fall into a black hole, and I said we don't know, and that's certainly true. But one possibility that's been around for quite some time is that maybe instead of hitting a singularity at the center of the black hole, you fall through it and come out in another universe. Well, a slight adaptation of that is, well, maybe you come out in another part of our universe. The big problem is, when you look at the physics of this, this wormhole is like a tube or a tunnel connecting two distant regions of space-time to provide a shortcut. The gravitational forces or fields involved in this wormhole are so intense that they tend to make the wormhole shrink. The throat of the wormhole would collapse and trap anything trying to get through. And so the trick is, if you're really seriously interested in turning this into a practical proposition, is to devise some way of keeping the throat of the wormhole open. And to do that, you need exotic types of fields that have negative energy and all sorts of properties which have never really been observed in the laboratory.
No problem for your quantum mechanic, though?
Exactly, no problem for the quantum mechanic. And so some of my own work has in fact been on the negative energy that quantum field theory predicts, and the use of this negative energy to keep wormhole throats open. So it's one of these sort of theoretical games that we play, and in fact it's quite curious historically that after Carl Sagan wrote this novel, he went to his friend Kip Thorne at Caltech and said, can you and the gang check out this idea? And they did it as a piece of recreational research, but it's actually spawned a whole industry, and there are people all around the world writing papers on wormholes, not just as devices for jumping from A to B through space in this manner, but also as time machines, because it turns out that if you can go through a wormhole to some distant place and then come shooting back at close to the speed of light the normal way through space, it's possible to get back to your starting point before you left.
Another good reason to keep the throats of our wormholes open, isn't it? Really?
Yeah, well, exactly.
Along comes young Einstein, wobbles the pedestal of Newton. When will another dazzling young scientist, he or she, come along and wobble Einstein's pedestal?
I have a hunch it's going to be pretty soon, and the reason for this is that gravitation is only one of four fundamental forces of nature, the other three being electromagnetism and two nuclear forces called weak and strong. And I think most physicists believe that these four forces ought to be integrated or unified into a single superforce. So somehow we have to draw gravitation, which has this very peculiar description in terms of geometry and the warping of space-time, in with these other forces that have more conventional descriptions. So it obviously is ripe for modification. Where I would say that Einstein's work will stand the test of time is in the special theory, the no faster than light rule, for example, the E equals mc squared, the weird effects that act when you go close to the speed of light with the space and time distortions. I think that's here to stay.
Will the next great equation be written on a single blackboard by a single hand and be a product of a single mind, or will it be the consequence of collective effort?
This is an interesting thing, isn't it, in the history of science? You look back and say what came out of the scientific culture and what was a matter of product of a genius. And I guess Einstein himself is supposed to be the archetypal scientific genius, beavering away on his own, coming up with great thoughts. Well, as I mentioned earlier, I think the general theory of relativity was largely a product of his own intellect, whereas the special theory, he drew upon a number of contributions from different people. Could anybody today command the subject of physics with the authority of an Einstein? I really don't know, because as you push back the frontiers, what you need to know gets more and more extensive, it gets harder and harder, the ideas get abstract, they get difficult, but in particular, the level of mathematics gets tougher and tougher. Einstein's often held up as a great mathematician, but actually he wasn't terribly good at mathematics. He really wasn't a mathematician by training. To formulate his general theory of relativity, he had to go to his friend Marcel Grossmann to teach him the necessary geometry to put it in this abstract form. What's happening now is that these subjects that I mentioned, like M theory and string theory and so on, demand not only a lot of 20th century mathematics, but some 21st century mathematics too. In other words, they're having to invent the mathematics as they go along.
And might they not need the assistance of one of those quantum mechanical computers we were talking about earlier?
Well, I don't think so, because my belief is that the fundamental laws of the universe are mathematically elegant and simple. So although they may be abstract, and although the branches of mathematics may be tough to learn, and difficult for humans to wrap their minds around, nevertheless, at the end of the day, I think they'll be elegantly simple. The point about computers and computation is that they're very good at speedily solving messy, complicated problems. So computers aren't very much help in this area.
In our next exciting episode, Paul, I think we should go chasing a cosmic butterfly.